everybody hear me? Okay. Can you hear me now? Yes. Good evening. We'll start. I think a few people are still stuck in traffic, but this is a very comfortable audience and we will start now. It gives me immense pleasure to introduce Professor Kathy Hunt, who, as you all know, is a chemist, and who will be speaking to us tonight about scientific advances by women researchers and the challenges they faced. This is an event organized by the Bridge Forum Dialogue in collaboration with the University of Luxembourg and the Institute of Advanced Study. I would like especially to thank Dmitry Fedorov for suggesting this special event. I would also thank Alex Tachenko. I would also thank Klaus Vögeler. And a very big thanks to the Banque de Luxembourg for the very generous help in providing this magnificent auditorium. Thank you very much indeed. And for the organisation as well, I would like to thank the Bridge Forum Dialogue and all the effort that has gone into organising this event, actually at much shorter notice than normal Bridge Forum Dialogue events. So again, congratulations and welcome to this audience. So Professor Kathy Hunt, obtained her bachelor from Michigan State University, then went on over the Atlantic to Cambridge University in the UK as a Marshall Scholar, and then returned to the USA as a postdoctoral fellow at MIT. And then subsequently, Michigan State University offered her and her husband 2 separate posts and enabled them both to have a career together in the same institution and in the same country, which I think is one of the themes that will come up in today's talk. Yeah. She has always been in the Department of Chemistry. She is by profession and vocation a chemist and is still a chemist. She was chair of the department for a term, 1998 to 2002, where she put her considerable energies into hiring senior faculty and making significant changes to the department. Since 1992, she has been a university distinguished professor at Michigan State University. She is here, and she has been here since September, as a distinguished fellow of the University of Luxembourg Institute of Advanced Study, the IAS. We are extremely honoured to have you with us, and I will now hand over to you.
Great. Well, thank you very much for the introduction. I'm extremely happy this evening to have the opportunity to tell you about a set of very important scientific advances that have been made by eminent women scientists, and I feel very greatly honored by the opportunity to speak as part of the Bridge Forum Dialogue. I'd like to start with an extremely familiar woman scientist, and that is Marie Curie. Curie put her discoveries in the service of humanity, and I think that's perhaps one of the most important aspects of her career. It's also the case that she is the only person to have received Nobel Prizes in 2 different scientific areas, one in physics in 1903 and one in chemistry in 1911. Marie and her husband Pierre worked in a shed to conduct their experiments. The shed was very poorly ventilated and it wasn't waterproof, but nevertheless they made tremendous discoveries there. Marie had the idea that pitchblende, which was a uranium ore, might contain additional radioactive elements beyond uranium. And she and Pierre worked to isolate these elements from pitchblende. They were present in very small quantities. So initially they started with 100 grams of material. That was nowhere near enough to isolate the substances that they sought. And eventually they were working with several tons of pitchblende ore. They isolated polonium in 1898, 300 times more radioactive than uranium. And then in December of 1898, they were able to isolate radium. You can see the half-lives of the various elements here. Polonium-209 has a half-life of 125 years. Radium, half-life of 1,600 years. Well, this is a picture of Marie Sklodowska at age 16 in 1883. Marie was very interested in education, but her opportunities were restricted because the universities in Poland were closed to women. That's a feature that will recur throughout this talk. Maria and her sister, Bronislava, were able to take classes at the Flying University in Poland, which was an underground organization that moved from place to place in order to evade the Tsarist police. In 1891, Marie came to Paris, where she was able to enroll at the University of Paris. She found lodging in the Latin Quarter, and it's said that there were times when she wore all of the clothing that she owned in order to stay warm. It's also said that sometimes she forgot to eat. Marie and her daughter, Irene, carried out scientific research together on radioactive materials. And in fact, Irene won the Nobel Prize in Chemistry jointly with her husband in 1935. So if you count the total number of Nobel Prizes awarded to the Curie family and give double credit when the woman and her husband both won, there are 5 prizes among the Curies, which is certainly a record that's very unlikely to be broken. One of the things that I wanted especially to stress in the presentation this evening is Marie Curie's service with the Red Cross as the director of the radiology service. I wanted to mention this particularly to honor Her Royal Highness the Grand Duchess of Luxembourg, who is the patron of the Red Cross, among many of her other humanitarian activities. Marie had a quotation here: "I resolved to put all of my strength at the service of my adopted country." It was a remarkable effort that she undertook to take 20 mobile X-ray units to the battlefront in France during World War I. Beyond that, she established X-ray instrumentation in 200 field hospitals. So it was an extremely important effort. Marie needed a collaborator to work in the field, and the first assistant that she selected was her daughter, Irene, who was only 17. Irene was able to take the X-rays of wounded soldiers and then from the X-rays carry out a mathematical analysis to locate the shrapnel and the bullets, sometimes with the skepticism of the field surgeons, but she was accurate in her location. Great advantage of this was that it made it possible to avoid radical surgery when the shrapnel or bullets could be removed more easily. So very important. There's a quotation, it's really from Susan Sontag, but the kind of bravery that Marie Curie showed has been called the transformative moral courage of an example. And I think that she showed that, and also Irene showed that, and all of the other women that Marie recruited to serve in the X-ray units showed that kind of courage. Well, this is a picture of one of the mobile radiological units with Irene staffing it. In order to run the radiological service, Marie had to learn how to drive, for starters, and she had to learn automotive repair, and she had to acquire a large number of generators. And then she had to arrange for the retrofitting of the vehicles to serve as the mobile radiological units. One of the really remarkable things about this is that it is estimated that over 1 million soldiers were treated with Marie's X-ray units. Additionally, she conducted the first studies using radiation to treat neoplasms. It occurred to her that the radiation treatments might be effective against cancer, and in fact they were, but these were the first. So I want to go from Marie Curie to someone that I characterize as a woman who knew how to enter a room. And I'm listing her as Hedwig Kiesler and Frau Fritz Mandl. This may not be someone who's very familiar to you, but you may know her better under the name of Hedy Lamarr because she was a Hollywood actress. And I guess it would be logical to wonder what Hedy Lamarr is doing in a talk about women scientists. But in fact, Hedy Lamarr invented a device that would permit communication between someone who is dispatching a torpedo and the torpedo itself while evading possible jamming by opposing forces. She obtained a patent for this, but her work did not become known really until the late 1990s. She got the patent in 1942. Her collaborator in this patent work, I think it's fair to say he was similarly avant-garde and similarly unconventional as Hedy. This was George Antheil, and there's a record that at the Paris debut of his musical works, Airplane Sonata, Sonata Sauvage, and Mechanism, a riot broke out. Man Ray, Pablo Picasso, and Jean Cocteau were in the audience. There's some suggestion that the riot may actually have been orchestrated. It might not have been spontaneous. His first really big work was called Ballet Mécanique, and this was originally scored for 16 synchronized player pianos, 2 grand pianos, electronic bells, xylophones, bass drums, a siren, and 3 airplane propellers. And a riot also broke out at the first performance of this work in Paris. Well, what led to the invention? First, in Vienna, Hedy had acquired some background information about the issues with torpedoes being fired during World War II. Normally, they were fired with wire guidance. And the reason for that was that if a fixed radio signal was used to communicate with a torpedo, that could easily be jammed, sending the torpedo off its course and causing failure of the operation. So Hedy had learned about that because she had married an Austrian munitions manufacturer, Fritz Mondl. She was 18, he was 33. It was an interesting marriage. Mondl often met with scientists and military technologists, and he had a very extensive library that contained books on physics and mathematics. So Hedy, when she had the opportunity, read a number of those books and was largely self-educated in the fields. Well, she had the idea that if one could send out a torpedo but hop between frequencies, then jamming would be much more difficult to accomplish because there wouldn't be a static frequency signal to be acquired. And it occurred to her, she was familiar with Ballet Mécanique, and it occurred to her that the mechanism that George Antheil had used to synchronize the player pianos, 16 of them, could be used to synchronize the signals and the frequency selection between the torpedo and the sender of the torpedo. So she faced a very substantial number of challenges. She originally attracted the attention of Fritz Mondl when she was performing as the Empress Elizabeth of Austria in a play at the Theater an der Wien. And Mondl was someone who wanted to keep the German influence out of Austria. So in order to attempt to accomplish that, he had allied with Mussolini. Hedwig's parents, I think, might have thought that the alliance with Mondl would help to protect Hedwig and also perhaps additionally to protect them. After they were married, Mondl, however, grew very jealous of Hedwig, and he would not allow her to leave their residence at Schloss Schwarzenau without his explicit permission. So the question arose, how did she manage to leave Austria then? Well, on August 25th, 1937, she was at a dinner with Mondl and his guests. She was wearing her Cartier jewelry of rubies and sapphires, and she left the dinner, disguised herself as one of the maids in the household, took the maid's car, drove to the Hauptbahnhof, and took the Orient Express to Paris, then a train to Calais, then a boat to Dover, then a train to London, and she arrived in London where she felt that she was beyond Mondl's reach. Well, there's also the question, how did she acquire the name Hedy Lamarr? The quick answer to that is that it was on the SS Normandy in the Atlantic, traveling from London to the US in 1937. In London, she met up with Louis B. Mayer, who was the founder and head of MGM Studios, the movie studio with the roaring lion. Well, he offered her a contract, but she felt that the amount was insufficient, and she turned it down, somewhat to the horror of her agent that she had met in London. But she arranged to travel to the United States on the same ship that Mayer and his wife were taking, the SS Normandy. On the first evening at sea, the story is that she put on a dark green gown and she stood at the top of the stairs heading for the ballroom. She waited until all of the eyes of the people in the ballroom audience were on her, and then she stepped down the stairs very slowly, still captivating the attention of the crowd. At the bottom of the stairs, she walked over to the table where Meyer and his spouse were and began to talk with them. And the outcome of this was that she negotiated a contract for about 4 times the amount that she had originally been promised in London, and she took that contract. It's also the case that it was Meyer's wife who suggested the name Hedy Lamarr while they were at sea. Well, so I'd like to shift now to a somewhat different topic, still connected with the work of Marie Curie, but putting in a bit of chemistry and nuclear physics both. This is the current version of the periodic table with 118 elements. It's possible that more will be added in the future, and in fact, there are people working to synthesize elements with higher masses currently, higher atomic masses. Well, there are element names that honor individual scientists, and I wanted to point out to you especially element 96, CM. In order to identify who is honored by element 96, it may be helpful to know that Cu was already taken for copper, and Cr was already taken for chromium, and Ce was already taken for cerium. So Cm is curium. Then there are a number here that you may recognize if you look at the names: Einsteinium, Fermium, Mendelevium, Nobelium, Rutherfordium, Bohrium, Roentgenium. Roentgenium is important to mention because it was Wilhelm Röntgen who discovered and produced X-rays for the first time. He won the very first Nobel Prize in physics in 1901 for this discovery, and obviously the X-rays that he produced formed the basis for the X-ray equipment that Marie Curie took into the field. Copernicum may be a little bit of a surprise because Copernicus lived many years before Mendelevium, but the significance of his contribution to the solar system, the heliocentric model of the solar system, was so important as to be recognized. Well, there's one here that's not labeled yet, and that is MT. I find that a lot of scientists do not recognize who is honored by the name MT for element 109. It's possible that here in Luxembourg, there are more people who would recognize that because there's actually a bus stop named for the honoree of element 109 in the same vicinity as the bus stops for Beethoven and for Leonardo da Vinci, and that is Lise Meitner. She was the co-discoverer of nuclear fission. She and a chemist, Otto Hahn, worked at the Kaiser Wilhelm Institute for Chemie in Berlin. The institute was directed by Emil Fischer. It took a lot of persuading for Fischer to agree to allow Meitner to work in the laboratory with Otto Hahn, and an agreement was reached that she could work with Hahn in the laboratory provided that she never entered a chemistry laboratory. Fischer was concerned that her hair might catch on fire. That was the explanation given for that. Well, Meitner faced a number of challenges beginning when she was quite young. Education for girls ended at age 14 in Austria. So Lisa had attended the Mädchen Bürgerschule, but she could not enroll in a Herrentöchterschule because of lack of financial resources. Hedy Lamarr had been sent to finishing school in Switzerland, but that was not possible for Lisa's family. So in 1897, Austria first admitted women to its universities. And in 1899, Lisa began to prepare for the Matura. There was a 2-year lapse because she had to wait for her older sister, Gisela, to prepare first. In 1901, Lisa took and passed the Matura at the age of 22. And 5 years later, she became the second woman to receive a doctorate in physics from the University of Vienna. I'd like to contrast the curriculum of the Mädchen Bürgerschule with the preparation that was required for the Matura. So Lisa had learned sufficient arithmetic for bookkeeping, but no mathematics more advanced than that. I know that currently the Matura contains questions on advanced calculus. I'm not sure at the time that Lisa would have taken it whether it did or not. But I've listed a couple of items here with asterisks because the coverage of those topics was rather superficial in the School for Girls. And you can see that not only was the list much longer to prepare for the Matura, but there were many topics that were not covered at all in her earlier education. She had 2 years to make up 8 years' worth of schooling. She studied with 2 other young women, and she had a tutor, Artur Servasi, who had just recently completed his PhD in physics at the University of Vienna. So she was well prepared for the examination. There were 14 students who took the Matura in July 1901 at the Akademisches Gymnasium, and of the 14, 4 passed. 3 were Lisa and the 2 women who were studying with her, and the remaining person who passed was Henriette Boltzmann, who was the daughter of the very famous physicist Ludwig Boltzmann. So it was a rather incredible accomplishment. Lisa had career successes, but then she also faced career challenges. Her collaboration with Otto Hahn began at the Friedrich Wilhelm University in Berlin. There, Meitner had to go in the back entrance of the building, and she was forbidden to enter the lecture rooms or the laboratories. In 1912, her situation improved somewhat because she moved to the Kaiser Wilhelm Institute for Chemistry, along with Hahn. In 1917, she and Hahn discovered the protactinium isotope, which is 231 protactinium. In 1926, she became the first female professor of physics in Germany. But in 1933, because Lisa was Jewish, her license to teach was revoked. And in 1938, she decided that she had to flee to Stockholm. There, she worked at the Nobel Institute. But in December of 1938, Otto Hahn and Fritz Strassmann triggered nuclear fission. Lisa had been working on this topic with Hahn for 4 years, but she couldn't be there when the final decisive experiment was run. However, in February 1939, she and her nephew Otto Frisch published the first theoretical explanation of nuclear fission, and in that work, they recognized the tremendous release of energy that would occur when nuclear fission happened. So her contributions were very significant. Lisa was nominated for the Nobel Prize 49 times and never won it. Otto Hahn did win it. So I wanted to mention some of the features of nuclear structure. This starts with an observation about the magic numbers of electrons. This is often covered in chemistry classes, that there are certain atomic numbers that confer unusual stability on the atoms. These are the Nobel gases, helium, neon, argon, krypton, xenon, radon, and oganesson, the heaviest element currently in the periodic table. The inert gases all have a filled p shell, so an added electron would have to go into the next higher s shell, and that gives these elements specific stability and inertness. In fact, the formation of xenon hexafluoride was the topic of another Nobel Prize-winning discovery because it had been thought that the Nobel gases were completely inert. So there are also magic numbers of nucleons. Certain numbers of protons or neutrons confer an unusual stability on atomic nuclei. These numbers are a little bit different from the numbers for electrons. And you can see that partly because I've highlighted the colors indicating the particular regions of the periodic table where these elements are found. Helium, oxygen, calcium, nickel, tin, and lead, especially stable. So the question was, what is it that confers the special stability on these materials? And in fact, it was Eugene Wigner who referred to them as magic numbers. So what explains these magic numbers? The person who accomplished that was Maria Geppert-Meyer, and she's shown here in a picture with her colleagues at the Argonne National Laboratory, photo from Argonne Labs. She worked at the Argonne National Laboratory from 1946 to 1960. And I thought it was very amusing. The photo caption on the Argonne National Laboratory website reads, "Maria Geppert-Meyer, fourth from the right, poses with her colleagues." And I don't think it would have been hard to figure out which one she was, even without that label. So Meyer was speaking with Fermi in his office, or her office, in Chicago. And he was interrupted because he had to go and take a telephone call. But as he walked out the door, he asked Maria if she considered spin-orbit coupling of the nucleons. And the story is that he returned very shortly thereafter, and she already had the entire explanation worked out. In fact, she told it to him extremely rapidly, and Fermi asked her to calm down and tell it to him a little bit later on. But Fermi taught it to his class the next week. And in fact, Maria was so convinced she had figured it out completely that she said in 10 minutes she knew she was right. She had finished her calculations. So this is her description of nuclear spin-orbit coupling, and I think it's interesting because there is a certain feminine touch in the description. She said, "Think of a room full of waltzers. Suppose they go around the room in circles, and all the circles are concentric, so they're enclosed within each other. Then imagine that in each circle you can fit twice as many dancers by having one pair go clockwise and another pair go counterclockwise." Well, that would take some really serious orchestration to accomplish if you could fit twice as many dancers that way, but it's true for the nucleons. Then add one more variation on that. All the dancers are spinning around like tops as they circle the room, each pair twirling and circling. But only some of the ones that go counterclockwise are twirling counterclockwise, and others are twirling clockwise while they're circling counterclockwise. And then the same is true of the ones that are dancing clockwise. So there's a famous saying by Niels Bohr that when you first hear about quantum mechanics, if it doesn't make you dizzy, you haven't understood it. But I would say that I certainly get dizzy looking at this explanation of nuclear stability. I wanted to say a little bit about her early work. In her thesis in 1930, she worked out the theory of two-photon absorption. So this is simultaneous absorption of two particles of light by a material. It couldn't be tested until lasers were developed, but in 1961, there was a europium-doped substance where two-photon excitation was definitely observed, validating her theory. Interestingly, all three of her thesis examiners either were or became Nobel laureates: Max Born, James Franck, and Earo Windaus. The unit of two-photon absorption is called the GM in her honor. So she faced challenges also. In 1930, she married Joseph Meyer, who was an American who had boarded with her family. He was hired at Johns Hopkins University, but Johns Hopkins had an anti-nepotism rule. It was very common in American universities, and that prevented Maria from being hired at the same university where her husband worked. So she had a position, but her position was officially to work with German correspondents at the university and not to work on physics. Joseph then took a position at Columbia University. There's some suggestion that people at Johns Hopkins were unhappy with him because of his involving his wife in his research. When he took the position at Columbia, Maria was offered an office but no salary. Then she obtained a part-time professorship at Sarah Lawrence College, College for Women, after her election as a fellow of the American Physical Society. These are two circumstances that normally would occur in the opposite order. She began to work on the Manhattan Project in 1942, and in 1946, Joseph became a professor at the University of Chicago. Maria was appointed as a voluntary associate professor, so that is an associate professor, a lower rank than Joseph's, and without any salary. Maria was finally appointed as a full professor of physics at the University of California in San Diego. That was in 1960. 3 years later, she won the Nobel Prize in Physics. It was probably one of the best appointments that the University of California at San Diego has ever made. And one of the things that's quite amusing to me is that when the newspaper in San Diego carried the news of her Nobel Prize, their headline was, SD, San Diego mother wins nuclear physics prize. I suppose there is some validity in that because it's useful for women to know that it's entirely possible to have children and also conduct research in physics, although it multiplies the challenges that are connected with that. So this is a quotation that I find just gives me chills, and that is, "We are star stuff." It's remarkable where the ingredients of our bodies come from. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. That's just phenomenal to me. Carl Sagan said that in his 1980 TV series Cosmos. His comment was, "We are made of star stuff, and the universe is within us." I think that's incredibly inspiring. There was one catch in Sagan's commentary, which is that the process for producing gold and heavier nuclei was not known at that time, and in fact not known at all until just recently. But it's been discovered that the heavier elements, in fact, from element 41, niobium, onward, up to element 118, all of the natural elements were formed, at least in part, in colliding neutron stars. Very heavy stars, very compressed. I think it's been said that a teaspoon of neutron star material would weigh as much as the Earth. So intensely compacted by gravity, but they can collide with each other. And a collision of the neutron stars was detected by the Laser Interferometer Gravitational Observatory relatively recently. And at the same time, optical signals and gamma ray signals were observed. And it was determined that it was this type of collision that accounts for the production of almost all of the heavy elements. And in fact, you can see from the color on the periodic table, the yellow color indicates the formation of the element by neutron star collisions. So I wanted to show this because it's an illustration from Norway, from the shipping company Hurtigruten, which also offers passenger cruises, showing the midnight sun not setting in Tromsø, Norway. So you can see the time lapse, even at midnight and 12:30, the sun has not gone below the horizon. But this raises the question, what is the composition of our sun? Until the mid-1920s, it was generally thought that the elemental composition of the Earth and the sun were essentially identical. And in fact, that's approximately true for some of the elements. Silicon, carbon, and the common metals are present in the sun. They've been captured from earlier nova explosions of other stars, and they're present in about the same relative amounts as on Earth. But hydrogen is more abundant in the sun than on Earth by a factor of about 1 million. This discovery was made by Cecilia Payne-Gaposchkin. She proposed it in her Harvard doctoral thesis, and she proposed it on the basis of spectroscopic studies that she had done of the sun, looking at the emission of photons in transitions of excited states of helium and hydrogen down to lower states. She was actually forced to characterize her results as spurious in her thesis, but Otto Struve later described it as the most brilliant PhD thesis ever written in astronomy. It turns out that early on, Henry Norris Russell was generally credited with her discovery, but later it was recognized that she had in fact made this discovery. When she completed her PhD thesis in 1925, women could not become professors at Harvard. In fact, I believe that the first woman professor in chemistry at Harvard was hired in 1979, so a very long time after 1925. But in 1958, Payne-Gaposchkin was named the Phillips Professor of Astronomy at Harvard. one of the things that's interesting about this to me is that I learned about Marie Curie probably before I was 10 years old. But I didn't learn about Cecilia Payne-Gaposchkin until I was already a full professor of chemistry. Next person that I wanted to mention, Emmy Noether. There's a children's book on Emmy Noether here, and she's labeled as the most important mathematician you've never heard of, which is probably true. Noether was described by Einstein as the most significant creative mathematical genius thus far produced since the higher education of women began. She developed a theorem that connects conservation laws to symmetries, and it's an extremely important result that helps us to understand why momentum and energy are conserved. This is a bit technical, but the features that I wanted to point out, the symmetry with respect to position or motion in space is what ensures that momentum is conserved. There's a symmetry also with regard to shifts in time. There's no evidently preferred time point or time coordinate for the evolution in physics, and that leads to conservation of energy. Symmetry with respect to rotation gives conservation of angular momentum. And there's also a symmetry in electrodynamics that's a gauge symmetry that leads to conservation of charge. So an extremely important and fundamental set of conservation laws derived from symmetry properties. I should also say that Noether was really an algebraist, and she developed the theory of Noetherian rings. The rings satisfy the condition that every increasing sequence of ideals has the largest element. And it's probably worth noting that the integers, the rational numbers, the real numbers, and the complex numbers are all Noetherian rings. When Noether was the subject of a Google Doodle, I pointed this out to my cousin, and he said that he had been in an antique shop recently, and he thought he had seen a Noetherian ring there, but it was out of his price range. So this is a woman who is an special inspiration to me, Philippa Fawcett. She's the first woman ever to obtain the top score in the mathematics tripos at Cambridge University. At that time, women could not receive degrees from Cambridge University. They could attend the lectures, they could take the examinations, but they couldn't officially be awarded the degrees. Well, it's interesting when the results of the mathematics tripos are announced in Cambridge, the degree candidates are read in order from top to bottom at the Senate House of Cambridge, and there's usually quite a crowd that gathers for this event. They start with the very top scorer, the senior wrangler, and then proceed all the way down to the last person who's classified as the wooden spoon. Well, when they discovered that Philippa had placed the highest, they faced a puzzle because their normal practice for announcing the order of the placement was to say between A.B. Jones and C.D. Smith to indicate where the woman had scored on the tripos. And when they announced the results for Philippa, they started out with the word above. And the crowd immediately broke into an uproar, and they managed to complete the statement above the senior wrangler, but she couldn't get a degree from Cambridge. She was able to travel to Trinity College Dublin, where she got an ad eundem degree, which is of the same degree category. She later taught at Newnham College, Cambridge, a women's college, and one of her students wrote, "My deepest debt to her is a sense of the unity of all truth, from the smallest detail to the highest that we know." And that is something that I think is a tremendous accolade for a person to receive. She died at the age of 80, and it was just 1 month after the grace that allowed women to be awarded the Cambridge BA received royal assent. So she lived to see women being able to take degrees from Cambridge. I wanted to mention next someone that I met when we were both about 25, and that is Baroness Ingrid Duboschi. Baroness Duboschi was awarded the Wolf Prize in 2023 for her creation and development of wavelets and harmonic analysis. These are used in digital processing. She worked at Bell Labs for an interval, and she realized that there was an issue with trying to provide accurate representation of pictures, but with a limited number of bytes of data. And she discovered that compactly supported wavelets, which are waves that are localized in space, could limit the amount of information that was required for data processing. This is used in the JPG 2000 standard. It's interesting to note that she and her team also applied their methods to restore the Ghent altarpiece from the 15th century. This is work that is attributed to Hubert and Jan van Eyck. And this is a slide showing the Ghent altarpiece. I think you can tell just from the slide the intricacy and the complexity of accomplishing the restoration, which she was able to do with her methods. She was also able to recover the words on the slide that are attributed to St. Thomas Aquinas. And beyond that, she's worked to determine the authenticity of paintings that are attributed to Van Gogh and to Rembrandt. So my next woman, this is quite a list of accomplished women scientists, but Donna Strickland, 2018, won the Nobel Prize in Physics, and she won it for her implementation of chirped pulse amplification. A chirped pulse is a somewhat unusual laser pulse where the frequencies are spread out in time so that the red light may reach an object before the violet light or vice versa. By stretching the pulse out with chirping, then the pulse can be amplified at that point and recompressed to give a very intense pulse. The result of that is an ultra-short, high-energy pulse. And I think it's worth observing that Donna received this prize when she was still just an associate professor in physics. She said it wasn't really the fault of the University of Waterloo. She had just never asked to be promoted. So Anne Luget won the Nobel Prize in Physics in 2023. Her work built on Donna Strickland's work using chirp pulses, but she carried a little bit further to produce pulses that act on the attosecond time scale. So it's 10 to the minus 18th seconds. And the significance of this is that when you can observe things on that time scale, it's possible to see the electronic rearrangement during chemical reactions. While the nuclei are still fixed, the electrons are moving around. So attochemistry is one of the most important discoveries, I think, and very well recognized by the 2023 Nobel Prize. This is just a schematic diagram that shows the production of the attosecond pulses. The significant thing that I wanted to point out here is you can see that there's a spread of the frequencies in the pulse, red through yellow, green, and then to blue. So she's employing the technique that was developed by Donna Strickland, but building upon it. Then I wanted to mention German Chancellor Angela Merkel. You may not think of her as a scientist, but in fact she got her PhD in theoretical chemistry, which is my field. She was awarded her doctorate in 1986. Her thesis was in quantum chemistry, and she published a paper, The Lowest Bound States of Triplet Boron H2+. That was the year the Berlin Wall came down. My research advisor for my PhD was the editor of the Journal of the Chemical Physics Letters Journal at that time, and he pointed out in a conference commentary that he had received this paper from Angela Merkel, and it was very good, so they published it, which I thought was interesting. One of the people that I wanted to point out in the photo, that's Angela, obviously, there. This was a conference that was held in the Soviet bloc for very promising young scientists in the Soviet countries. Well, the person to her left is my colleague, Piotr Piecuk, who's in my department now. Grew up in Poland, but moved to the United States, and I was actually fairly instrumental in hiring him. I'd also want to point out her paper on BH2+ was published the year the Berlin Wall came down, 1989. She entered politics immediately the next year. Barbara McClintock is a very interesting scientist who won the 1983 Nobel Prize in Physiology or Medicine for her work on the genetics of maize. I know she's the only woman to have received this prize solo without other collaborators, and I think she may in fact be the only person to have received this prize solo. Her work was on the genetics of maize, and that seems a little bit far from physiology or medicine, but I'll show in a moment how the connection occurs. So her question was, with these patterns in maize, how do they develop? And her answer was jumping genes, to put it colloquially. At first, no one believed her. It's interesting, McClintock was very interested in going to Cornell University to study botany, and her mother opposed that because her mother felt that if she had a college education, she would become unmarriageable. Well, her father apparently prevailed, and she was allowed to take her bachelor's degree at Cornell University and then subsequently master's degree and PhD. But she couldn't teach at Cornell. Cornell would not hire women. And so she got a position at the University of Missouri, where she was an assistant professor. Her exploration of corn cells showed that they're actually quite different from human cells. The chromosomes come in groups of 3 rather than 2. And that means that the genetics is a little bit more complicated to unravel. There are 2 alleles specifically, two genes that control the color of the kernels. One has a pair, either C' or C. C' is the dominant one, and if the kernel has the C' allele, then the kernels will be pale yellow. But if the kernel happens to have the C allele, that's recessive, and that permits color to develop. Then there are 2 color genes, capital BZ and lowercase bz. Capital BZ is the dominant one, and it produces purple kernels. The lowercase bz is the recessive one, it produces brown kernels. So Barbara carried out mating experiments where she combined female corn that had capital C and lowercase bz alleles in it. That would permit color, but it would be brown. And then she included a male corn cell chromosome, C', capital BZ. Well, C' should produce pale yellow kernels always. The capital BZ could permit purple kernels. And what she found was instead of having what she expected, the outcome of the dominant C' allele that would produce yellow, pale yellow colored kernels, they were often mottled, and there were spots on the kernels. So she had to explain how this could be possible. Well, how could this happen, and how could she figure it out? There's a quotation from Louis Pasteur that in the United States is usually rendered as chance favors the prepared mind. Well, she had background that helped her explain this. She was the first person to describe the cross-shaped interaction of chromosomes during meiosis. And she and Harriet Creighton proved that chromosomes could cross over during meiosis so that genetic information could be exchanged between the chromosomes. And the chromosomes that we each inherit are not exclusively chromosomes from either parent, but can be mixed and have genes from both parents on a single chromosome. McClintock also showed from experiments on X-rays that chromosomes could break and that the broken segments could rejoin. And then she made the final clinching discovery that there are interacting elements in the chromosome that she called DS and activator, DS, dissociation, and AC. If activator is present, then DS can actually move along the chromosome, so the jumping gene designation, and it will result in breakage of the chromosome. And it was that allowed the C allele to be expressed instead of C', and the kernels could gain color. Well, interestingly, there was so much opposition to her ideas that she completely stopped publishing on this topic in 1953. And then by 1983, she won the Nobel Prize in Physiology or Medicine for this discovery. The movement of genes along the chromosomes is something that's very important in the development of all creatures, really. So many others. So today, I took this illustration of a T-shirt on Women in Science. If you're interested, you can actually obtain it from goodteacherlife.com. It shows a number of women. I've listed on the left the women that I've discussed so far today. And then on the right, an entire group that I haven't discussed. But I did want to mention one more woman who is very interested in biology and medical science and made a tremendously important contribution, and that is Katalin Karikó. Karikó and Drew Weissman received the Nobel Prize this year for their work on developing messenger RNA vaccines. Initially, they had the problem that when they tried to develop vaccines based on messenger RNA, there was always an inflammatory response that was provoked. But they discovered that if they replaced uridine in the messenger RNA with pseudouridine, then inflammation did not occur. And they were able to package the messenger RNA in small droplets of fat as a delivery mechanism. It's interesting, Karikó's career also was not in any way a straightforward advance. She was originally living in Hungary, and she and her husband left Hungary with their 2-year-old daughter, and they smuggled a total of 900 pounds in their daughter's teddy bear. They sold their vehicle to obtain the money. Karikó became a postdoctoral fellow at Temple University in the US, and then she moved to the Uniformed Services University of the Health Sciences, which is in Bethesda. After that, she was hired by the University of Pennsylvania as an adjunct professor, which would enable her to move to the tenure track and eventually become a full professor. In 1990, she submitted her first grant application to work on messenger RNA in gene therapy. And unfortunately for her, the timing was not good because messenger RNA had really fallen out of favor in the United States in science. And so it was not possible for her to succeed in getting grant funding, even though her proposals were exceptionally good. She was offered the opportunity to remain on the track to a tenured professorship, but under the condition that she give up her messenger RNA research. And she decided rather to accept a demotion in order to be able to continue her work on messenger RNA. Well, in 1997, Drew Weissman was hired by the University of Pennsylvania as a professor of immunology, and Karikó was able to work with him. Nevertheless, despite the fact that he was a professor, Weissman said we had to fight the entire way in their research. Well, in 2013, Karikó left Penn to become a vice president of BioNTech RNA Pharmaceuticals. And as she left, she told her boss, in the future, this lab will be a museum. And actually what she said to him beyond that was, don't touch it. So 10 years later, she and Drew Weissman shared the Nobel Prize in Physiology or Medicine for their work. So I'd like to express my extremely deep gratitude to the organizers of the Bridge Forum Dialogue for the opportunity to speak to this very distinguished group and to describe the accomplishments of a remarkable set of women. I am very greatly honored by the opportunity to speak here. At the University of Luxembourg, I'm very grateful to the Institute for Advanced Studies for a distinguished grant which has made my visit possible. And I'm very grateful for the wonderful hospitality of the Department of Physics and Materials Science and all the members of the department. I found a tremendously exciting intellectual environment here, and I really look forward to continuing the collaborations after I've returned home. So again, thank you very much.
Thank you very much indeed, Professor Hunt, for this very, very wide-ranging and I think very inspiring talk. And I think it's lovely to start with a name that everybody's familiar with and to introduce more and more women scientists and to really see not only their amazing careers, but also the obstacles that they've had placed in front of them in pretty much every political system imaginable as well. And I think that's something that is, extremely thought-provoking. We've received some questions in advance, so what I propose to do is to run through the questions we've already received and then to open up to questions from the audience, because I'm aware that we have some people watching online as well. So thank you very much indeed for the people who sent these questions in. We have a very, very long first question, so what I've done is I've split it into 3 sections because the person who sent the question in very helpfully split it into 3 sections. So thank you, the person who sent this question in. TheScience.org has published 3 trouble spots facing women in science. First, a sense of belonging. Across many fields and career stages of academia, women report a lower sense of belonging compared to their male colleagues, which is problematic because if a young woman feels that she doesn't belong somewhere, then she's not going to stick around. She's going to take every single pitfall as a statement that, well, it's not for her. So the question is, what do you think? Have you experienced or witnessed any of these situations? Do you have any ideas about how these situations could be remedied?
I think a comment that I probably should make first is that when I was an undergraduate at Michigan State University, I took approximately 60 different courses in the pursuit of my bachelor's degree. And among all of those courses, I did not have any women faculty members teaching the courses in physics, chemistry, mathematics, computer science, or biology. And in fact, I had only 2 women professors altogether, one in Roman history and one in Indian philosophy. So 2 out of 60 is pretty low representation. One of the things that I wondered about when I was an undergraduate was whether it was possible for a woman to succeed in science. And now seeing a very large number of women in the audience, and probably quite a few of them scientists, I think that this fear is no longer operational for people. But I certainly wondered about it when I started. Later, I began to realize as I studied the biographies of famous scientists that I might just as well have wondered if it was possible for an American to succeed in science, because such an overwhelmingly large number of the famous scientists were European, with some Indian as well, and people from other countries, other continents. But really very few Americans. J. Willard Gibbs and Richard Feynman come to mind, Julian Schwinger. But early on, there were not so many. So I think that I always had a sense of belonging in that people were very helpful to me and collegial. But I did wonder, because of just the small numbers of women, whether there was some obstacle that I hadn't found out about yet.
Thank you. So the second part of this question, which is another one of these 3 trouble spots, women often face harassment and bullying in daily work life and encounter unprofessional behaviour more often than men. Sexual harassment in particular remains a pervasive issue in many branches of academia, research, and other aspects of the sciences. Archaeology, for example, has spent a very long time exploring those problems. In 2018, the National Academies of Sciences, Engineering and Medicine released a comprehensive report about sexual harassment in STEM subjects, which stated that many female students, up to 50%, depending on the study, experience some form of sexual harassment directed at them by faculty or staff. And obviously the consequence of that is they're really not going to stick around. And again, basically over to you. Have you witnessed anything of this sort? Have you got any ideas again about how these situations can be dealt with? I mean, I've just cited archaeology. There are many subjects where these are problems.
At this point, it probably looks absurd, But yes, I did experience instances of sexual harassment in my career. I'd like to say very clearly that I experienced none as an undergraduate, and I never experienced any from the people who were my research advisors or my collaborators in research. But I did experience 2 incidents in my lifetime, and rather amazingly, one while I was already chair of the Department of Chemistry at my university. So how to prevent that? I think that awareness has been raised much more strongly than it was in the past. And so I look forward to these incidents declining very substantially. I think that it's less likely now for excuses to be made for someone on the grounds that they have scientific eminence, even if their behavior is not desirable.
I think I would say also that one of the things to challenge are rules of silence. One of the things that I'm struck about in the university where I work now, which I was less aware of before because I was very much within my field, which is actually the humanities, which is much stronger on women in many senior roles, is that you get laboratories. And you get laboratories where you don't know what's going on in that laboratory. It's a world to itself. Very often those laboratories will be extremely male-dominated. It's not uncommon to come across just one woman, perhaps, in the lab.
Yeah.
And the stories that emerge out of those laboratories can be absolutely shocking. And that's one of the things, that's one of the actions that every single university has got to be aware of, because there are hierarchies, there are rules, there are boys' clubs, there are senses of what goes on in a team-building environment. And I'm stating laboratories, they can be workshops, they can be field work, etc. Those things are particularly to be looked at. So I think answer 1 was about role models and literally having more women in roles of teaching and making women feel that they are part of that community. The second answer is to really introduce very strict measures, one of which is bystander awareness training. That when somebody is witnessing an event, to intervene immediately and to report, and not to feel pressurized into thinking, oh, sure, it's just a joke. No, it's not. It destroys careers. And I think that's extremely important. So we'll go on to the third trouble spot, which is women are paid less than men. And also women, yeah, that's true. And it's a fact. And I remember when I was a young lecturer, we used to tell each other this, and it seemed clever at the time. Like, never ask anybody what they're paid because you'll go mad. Yeah, and it was between departments, and it was actually, we didn't see it as a gendered issue. There were other issues as well. But there is a simple fact that there is, and this question leads to other things. Women are rewarded less often than men. It's very interesting to see that at least one of the women scientists, I think 2, were actually pressurized into saying that their work was false or worthless, so that somebody else could get the credit. That's fascinating. Because, of course, when you're looking at prizes, you're also looking at making a living and developing your own laboratory and things like that. So just over to you. Any ideas about that particular problem?
Well, I'd rather not address the salary issue, actually. If I can skip that one, I will. But I will say that I am absolutely delighted to be here because one of the challenges that I think women face in science especially is that the opportunity to travel and speak at conferences is somewhat limited by childcare responsibilities. I know there were parts of my career during which it just wasn't practical for me to go and speak as often as my male colleagues were able to speak elsewhere. And those things do build on each other because the more evident you are in conference circles, the more likely you are to have additional opportunities to speak, which then causes the grant referees to be familiar with your work, which has beneficial impact on your successes with grant proposals. And so it is a kind of snowballing effect. I think that there have been efforts recently to ensure that a greater fraction of the speakers at conferences, especially in my area, are women. And I think that will have a very beneficial impact down the road.
There was a very interesting campaign called Look at Your Role Male panel, which I think was on one of these old sort of platforms, and it was interesting because you could just fill it endlessly with all male panels, and just one woman in the corner holding something. I mean, it was it's something that obviously, unfortunately, I still do now. Not only in academia. We'll move on to another question. This is another question from somebody else. What is your perspective on how schools and policymakers, you might want to split these two, could play a role in encouraging more girls to pursue the scientific path after secondary education? Do you have any ideas?
I think one of the most important things is for girls in the schools at an early age to have an opportunity to experiment with scientific apparatus and to run their own experiments. For example, in my daughter's school, the students were encouraged to develop science projects for a fair in the spring, beginning in kindergarten. So my daughter did a project on how fast things would go down a slide, and she had a stopwatch to determine with various objects how rapidly they went down the slide. Then in first grade, she did an experiment that we called Rainbow Liquid, which used corn syrup. And if you illuminate corn syrup, because the molecules have chiral symmetry, there is a rotation of the plane of polarization of the light. And she was able to use polarized lenses from sunglasses to observe this rotation by looking through the glasses and tilting the lenses from place to place, see different colors emerging. Probably the most radical experiment was the one that she did in third grade, trying to figure out how magnetic force varied with distance. This didn't work out so well. It caused very heavy magnets to be shot across our living room. But I think that the opportunity to do that sort of work is very important. When I was in high school, my biology teachers entrusted me to work actually alone, which wouldn't be permitted anymore, but to work alone in the laboratory on a project in bacteriology. I was attempting to take E. coli that were resistant to streptomycin and transform other E. coli to make them resistant to streptomycin. Probably not the best project to be recommended at this point, but the opportunity for independent research was really important. There's so many exciting things in science that can be shown, and I think there's a great program of inviting scientists into the elementary and high schools to show some of the dramatic presentations, and that tends to intrigue people about science. And then if they can be encouraged that they can succeed going forward, that will, I think, help to build up the number of women.
Thank you. There's another question which starts, I think, we always say avoid yes-no answers. Do you think the structure, career path and mobility demands in academia is designed favourably towards men?
Well, probably accidentally, in fact, because initially mostly men were following the career path. It is a challenge. I was actually tremendously fortunate in this regard because I went to the University of Cambridge for my PhD, and the standard PhD period in Cambridge is 3 years. So I completed my PhD in 3 years. I wasn't certain initially whether I could do that, but I had taken graduate level courses in chemistry, physics, and mathematics at Michigan State, so I had the background that I needed to make that possible. And then my husband was a postdoctoral researcher at Harvard at the same time that I was at MIT. Michigan State let us know about the availability of 2 positions, and so with 5 months of postdoctoral experience, we accepted the position at Michigan State, and we arrived there with a total of 10 months of postdoctoral experience. The offshoot of that was that I actually became a full professor just 2 weeks after my daughter was born, and that's a very unusual, and I'm very grateful for the possibility to have that happen. But for many young women, there are extreme challenges of combining motherhood with the early stages of careers, and especially for assistant professors who have a limited period of time to establish themselves, to be awarded tenure, and then to be able to continue. So I'm not sure that I have a resolution to this. My university currently offers a delay of the tenure clock for women and for men when the family has children, so that they have a 1 year extra interval to work on establishing their national and international reputation and earning tenure. That's certainly a step in the right direction. What exactly can be done beyond that, I think, is still a challenge to be figured out.
I think one of the things that strikes me is that the next question is about the university, but a lot of universities, for example, will try to support somebody, usually the mother, who has children under the age of 5. It is a fact that actually babies and very young children are more easily taken to conferences, if you have help, than the older ones who have schools, who cannot be left alone, who have clubs to go to, football to play, etc. It actually gets harder over the age of 4 or 5 when the child starts regular schooling. And there's an aspect to this as well, which is to think about the life cycle of the academic, and that it is difficult to travel, it is difficult to go to conferences, it's difficult to do all the things that actually became easier with COVID, interestingly enough, because you were doing a hybrid conference and you could actually see somebody talking with a child in the background, and it was normal. And so there are some things that actually need to be challenged in terms of the life cycle of the academic, that actually as kids get older, they are not necessarily easier. And a whole group of us used to talk about going to conferences to catch up on sleep, which does happen. But I think those are things that need to be considered. Flexibility, hybrid options. There's a kind of change of culture that's needed, which is important. The next question, we'll touch on this one quickly because this is your evening. Is how would basically, how would you describe the state of the gender balance among the academic staff of the university, broken down by seniority compared to other research facilities in Europe? I'll quickly deal with the university as the University of Luxembourg, but then for you it's academia in general, globally. Very quickly for the University of Luxembourg, we are extremely typical. Despite we're being a young university, and we have on average about 25% female staff, if we're looking at professors, etc. An example of what we have is a classic example of the leaky pipeline, as it's called. Many women at the start, bachelor programs full of women, okay? And then it goes like that, and the pipeline starts to leak women everywhere. And the big leakage is at postdoc level. Okay, so if you look at the way that our university looks for the moment, and obviously it changes according to staffing, we have an evenly balanced, nearly rectorate with male and female representation. We have 3 female vice rectors and so on. One step down, we have a management team of 3 deans and 3 directors, of whom 1 is a woman. One step down from that, we have heads of department. We started out with 12 heads of department nominated in 2019 when departments were created. You could only be a head of department if you were a full professor, a professeur ordinaire. The result of that is we had 1 female head of department. And now, 2023, we have 2. That's your leaky pipeline. That's the fact that actually the upper levels of seniority, and it's exactly that about role models, are okay, but actually to get there is incredibly difficult. And if that sounds bad, it is worth bearing in mind for the surrounding countries, this is actually very, very typical. Roughly Germany, France, the Netherlands, Belgium, we're looking at about 25% of women in academic environments who are professors or who have stable posts. And in some sectors, 25% full stop. We do have 1 department in our university which has no women professors. And we are all in agreement that is absolutely unacceptable. But when you look at the geographical region, even countries that have had very energetic programs for getting more women, targeted recruitment, changing some of the regulations about gender equality in order to target and to recruit women, which has actually been happening in the Netherlands, in Belgium, etc., it's still not budging. It's not shifting because of that leaky pipeline, because women leave academia quickly at the early stage of their career. They cannot get onto that treadmill. And I've just described it as a treadmill, not a ladder. Yeah. So I think all of those things are important. Right, I'll hand over to...
So I'd like to start actually by tracing a little bit of my family history. My maternal grandmother went to college in West Virginia, but she came down with the Spanish flu in 1919, and so she had to drop out. My paternal grandmother was a college student at Butler University in Indiana, and my grandfather was also there. My grandfather became attracted to her to begin with because she was the only student who could beat him out at Latin. And so he paid attention to her. When they had completed 2 years at Butler, he decided he would like to get married to her eventually. And so he wanted to go and tell her parents that. And she was trying very hard to dissuade him. But he definitely wanted to let her parents know. When her parents found out, they said if she was just going to get married, then she didn't need a college degree, and they pulled her out of college. My mother was a high school student in a small college town in Ohio, where she was not allowed to take the physics course in high school because the physics course was reserved for boys. And this combination of events, my mother went on to complete a college degree and took calculus during college, which is a little bit unusual in that era. But this gives me the perspective that it may be a question of generational change to have the ideas adjust. If you look at my department, the percentage of women is about 27% in chemistry, about 27% in physics at my university. So it is comparable to the University of Luxembourg. If you look at just the pictures of my department, everything looks great. We have, well, great in a sense. We have 14 women out of 48 faculty members. But when you look at the breakdown, 3 of the women are full professors, and 2 of the women are associate professors. All of the other women are assistant professors, and in fact, 6 of them were hired just last year. So the number of women, their visibility, is not necessarily representative of the overall situation at the university. And in terms of the leaky pipeline, I can say that I started at Michigan State in 1979. Since the year 2009, I've been the only woman faculty member who started in our department as an assistant professor and is still there, even though we hired many women in the interim. Several of them moved to other universities. Several of them just quit. And so it's been distressing to me to observe that pattern, and I'm hoping that with our large group of assistant professors now, that will be changed very significantly in the future.
Mm-hmm. Thank you. I think this leads us on to this question, which is actually, how does the underrepresentation of women in leadership positions in science and the technology industry. It's been interesting seeing what's been going on in OpenAI in the past few days, which is kind of interesting as well. You've got a female CEO who appears and then disappears very quickly. We don't know actually what the reality is on these reports, but it's interesting. Does this impact innovation and progress in this field? In terms of what you've been discussing now, let's move away from the leadership side and actually look on simply the presence and the belonging of women in these sectors. Is innovation and progress being impacted by these problems?
I think that's a really difficult question to answer because the net progress in science depends on, to a very heavy extent, on the total number of people pursuing science. And so if it's just a question of replacing a man with a woman, there may be some advantages in that there may be some differences in the approach to problems that women take. And certainly everything that I've described this evening is showing some quite original and unusual ideas that women have held. But my preferred solution to that really would be to expand the number of positions in science and technology and perhaps as a consequence, increase the percentage of women who are employed in those areas. But I think it's important for there to be opportunities for everyone.
So the last question we received actually is a little bit different, which is in the past 10 years, 15 years, a lot has been done to try to readdress the balance and to change things. And this has caused some frictions. It's caused some confusion as well, that people feel that, there is targeting recruitment, etc., but then what happens afterwards? And could you suggest how to positively adapt to these new environments or to these new strategies and policies, because it is challenging.
Right. Yeah. So I think there are a couple of steps that are important that can be taken to improve the opportunities for women, and one of them is to provide support all the way along in the academic career. I was very fortunate to have an undergraduate research advisor who encouraged me all the way along and pointed out, in fact, that one of my biggest problems was a lack of self-confidence, which may have resulted from the absence of women models around me in the university. But he was very encouraging to me. All of the people that I interacted with later, my PhD advisor, my postdoctoral advisor, the chairman of the department who hired me, were very encouraging to me specifically, and I think that made a great deal of difference. It's also the case that I was hired in an era when affirmative action meant that one attempted to advertise the positions that were available to women and encourage them to apply, but there wasn't any particular advantage given to women in hiring. And I think the difficulty with that is that it may be difficult to have the patience to allow for the generational change. There are many people who support having programs that are open only to women. I know there's certainly an argument to be made for that. Personally, I wouldn't favor that, which I know would upset quite a few people, and I'm sorry about that. But I think it's important for the opportunities to be available to everyone without restriction based on personal characteristics. So that is only my personal view.
Thank you very much. I will hand over to the audience. We have 2 microphones here. That's great. Thank you. Thank you. So,
Professor Dr. Hunt, it's an honor to meet you. Thank you for gracing us with your presentation. It was fantastic.
Thank you.
I repatriated to Luxembourg after 16 years in Kentucky, and I'm fascinated by high school STEM academies in the States. And in Kentucky, you have one of the finest boarding schools for gifted and talented public high school students, Gatton Academy. And they have a partnership with Western Kentucky University. And I'm wondering how you would, or if you already partner with public high schools, possibly in Luxembourg, possibly in Europe, but maybe closer to home in the States. If you have similar academies in Michigan that Michigan State, go Spartans, has an eye to help focus on women maybe as much as men.
Yeah, that's a really great question. In Michigan, we don't have a specialized science and math academy for high school students. I know that aside from Kentucky, there's also one in Illinois, and my university recruits quite a few people from the high school in Illinois. There's also one in North Carolina, which my niece attended. And I think these provide wonderful opportunities for really advanced work in STEM fields for everyone who can attend the academies. So in terms of the efforts that I've put in my university, we have a program for 6th grade girls, which would be girls typically of 11 years in age, to come to the university and try out a set of experiments and have demonstrations. And we also send people into the schools to give demonstrations and talk about careers in science. We have in the US a competitive operation called the Science Olympiad, where students may either learn specific topics to a much greater depth than is taught in the schools, or conduct experiments, prepare apparatus. In Michigan, some of the experiments involved creating a musical instrument, building it from scratch. Some of them were musical, some of them were instruments, but not musical. There were challenges to produce a Rube Goldberg device that would take a marble and run it through the device, but keep it from reaching the floor for at least 60 seconds. It's more challenging than it sounds because gravity is very powerful and has a very high rate of acceleration. So those things, we also have at the university a children's college for elementary school students at the end of 4th and 5th grade, where they can come and take a 2-week program in the scientific area. So my daughter was among those who took a 2-week course in astronomy, which was quite interesting. We try to do things to involve young people in science. One of the 2 most recent publications that I have, I wrote with a group of students who were high school interns. And I had a group of 4 students working with me in quantum computing the first year, and then the second year, a group of 11 working in quantum computing. And of the group, we've had 2 papers so far, one on the Bell inequalities and the Clauser-Horn-Shimoni-Holt inequalities, subject of the 2022 Nobel Prize in Physics, but we were investigating it on quantum computers. And then another one on the entropy of so-called Schrodinger's cat states, which are superpositions of states where all the qubits have value 0, all the qubits have value 1. And I have a third group who worked on Shor's algorithm for factorizing integers. A potentially serious problem because the use of integers that have just 2 prime factors has been very important in encryption and credit card security, bank security. And if you're able to break the number down into its prime factors, you can break the code. But at the moment, there's not really a hazard from quantum computers because of fault rate and limits on the number of qubits. But that is something that is of concern for the future. The first people to factorize any integers using quantum computers determined the prime factors of the number 15. And then later this was extended to 21, then 35. My group, using the quantum simulator, factored 39. But this is a very far cry from anything that would be used in encryption. So not an issue at present, but I think a very good experience for the students. And then they went on, when they went to university, to work in laboratories and have summer internships in places where the quantum computing was actually in use. So of the group, I had 3 women out of 11, so not a very high representation, but still they were very happy with the work they were doing. And I think they were treated collegially and on an even basis by the male students, which is a really important feature.
Thank you. Any other questions?
Good evening. I would like first to thank you for this very enriching and inspiring presentation. I will discuss about two points. The first one is a comment from my own experience. I'm a student in electromechanical engineering from Belgium. And what I can say, of course, is that we are not a lot of girls or women doing this. And here I'm doing my Erasmus in Luxembourg in energy engineering. And what I can say is that we are not a lot of girls doing this. But I wanted to share this positive thing is that I never felt in my student life this injustice in genders. I always felt comfortable with my studies, with my
Yeah, that's good.
environment. So I
Great.
wanted to share it because I think that this is a very positive thing. Of course, my opinion cannot be generalized, but even if it's at a small scale, well, it's not inexistent. So this is this positive vibe that I wanted to share. And for the second part, it's a question for students like us in science, applied science, engineering. If we have this desire of share our ambitions and also inspire other people, well, what would be your best advice for that?
One of the things that I have observed is that the number of women in science and engineering has tended to move much more in the direction of equality at the undergraduate and now at the graduate level. When I was a student, it was not so common for a woman to be in a science field. And I had courses in which I was the only woman student. And now I imagine that you've not had that experience really at all, which is really encouraging to me. I taught a course in statistical mechanics and chemistry, which had students from chemical engineering and chemistry in the course, and in fact the majority were chemical engineers. And there was essentially gender parity in that course, which is really encouraging to me. I feel that the equality was attained more rapidly at the undergraduate level than at the graduate level, but now it's being attained at the graduate level. And so I think there is serious hope of progress for the future, so that the representation of women will eventually be at the level for the interest that women have in science, and without any suppression of interest by concerns about the difficulties of being a woman. I think it's wonderful what you're doing, and I think just being in the course and enjoying the work that you're doing is one of the best ways to communicate the opportunities and the great pleasure of doing work in STEM subjects to other women and to men as well for the future. So I think that's just wonderful.
Do we have any other questions? Yes.
Very thanks for this very nice talk, and you discussed on several women researchers who came from different scenarios and how they battled. And in between your talks, you also mentioned about feminine touch in research. And that's good that we are discussing on equality, which is very good. But there are differences that can be very well capitalized. And I've seen in my home, my mother, her vision, and how it actually helped my dad's work. And these kind of things should also be talked about. I mean, I would like you to elaborate more on this, on how the feminine touch in the research would be very good and can yield wonderful results.
There was a stereotype many years ago in astronomy that women were best suited for very tedious work, analyzing spectra. And so one of the women that I didn't mention, Annie Jump Cannon, is the person who established the letter classification of stars. She was able to do this because she had access to all the spectroscopic data at the Harvard University Observatory. And I think that things have evolved now so that people recognize that it's not at all the case that the women should be limited to doing the more boring classification type of work, but can actually be significant help to their spouses. When I think about examples that I know of, Per Olav and Nanny Frohman were both scattering theorists and in Scandinavia, and did extremely important work on modification of the Wenzel-Kramers-Burgon approximation for solving the Schrodinger equation. Ruth Lyndon Bell was a very inspiring person to me when I was a graduate student. She was a faculty member at the University of Cambridge, and at that time there was only one professor. Everyone else in England was not a professor, was a reader or lecturer, senior demonstrator. So she was not the professor, but she was the equivalent of a professor in the United States. And her work was originally in nuclear magnetic resonance. Then she moved into molecular dynamics. And Ruth was eventually able to obtain her own professorship at Trinity College in Northern Ireland. But along the way, she also helped her spouse, Donald Lyndon Bell, who is one of the people who developed the current theory of the formation of galaxies, because the same ideas of molecular dynamics that she employed to chart the motion of molecules and liquids also could be used to describe the large-scale motion of stars during galaxy formation. So yes, I think that's a very important opportunity. And certainly, my husband and I talk about scientific topics all the time and provide each other with inspiration and also sometimes aggravation. so yes, it's very important. Thank you for bringing that up.
Thank you. Do we have any other questions? Yes?
Thank you. My name is Helen. I'm the last year PhD student at the University of Luxembourg. And actually the topic that we touched today is very relevant to my future, let's say. As Professor Leglu said, the leakage starts at the postdoc. Mm-hmm. And exactly, you know, I felt it this year. I started traveling all around to presenting my papers during the summer at the conferences. And each conference always had a key seminar that covered the future of women in the science. And there are a lot of papers cited there, but there were a couple of challenges that I never thought about and kind of brought a fear inside to me. The first one is that, maybe you know the answer, there is a research that claims for women in Europe, it's more difficult to overcome this stage from the PhD to the postdoc or associate professorship, while for the women in the United States, it's vice versa, more difficult to become a tenure professor rather than a postdoc. So my first question is, why is it like this? My second question is the following. So I have this fear now that if I choose academic path, I will have to fight. I will have to spend more efforts, time to prove the society who I am. And it makes me think now which path to choose. I love teaching. When I teach, I share my energy with students. I got wonderful feedback. And this is basically that always motivated me to never hesitate my choice about the future in academic. But now, these are two questions. Thank you.
Yeah, well, thank you very much. I think I can say for sure it is not easy. However, I really strongly encourage you to continue in academia. In the United States, actually, it's typical for a person to complete several postdocs before taking a faculty position. In fact, my colleague Piotr Pietrzuk that I mentioned, who was seated next to Angela Merkel at the Conference for Young Scientists, went to the University of Arizona as a postdoc, then returned to Poland, where he had a beginning faculty position. Then he went to Waterloo in Canada, where he had a postdoctoral position. Then he went to Toronto, where he had a postdoctoral position with John Polanyi. Then he went to the University of Florida, where he had a postdoctoral position with Rodney Bartlett, and then finally we hired him. So that's probably one of the longest postdoctoral trajectories that I know of. But it's very common in the US now for people to do one postdoctoral position. It gives you the opportunity to broaden your background and gain experience that's different from what you've had as a PhD student. And it's not really uncommon for people to do 2 postdoctoral positions. 3 is still pretty uncommon, but it's a great advantage. My postdoc was shorter than I planned. My husband and I had both planned to do at least 2 or 3 years as a postdoc before starting a faculty position. There were certainly some challenges connected with that, but it was still a great benefit to me. And so I think that should not deter you from pursuing an academic career. And I especially hope that since you love teaching and you like to communicate your energy and your enthusiasm to your students, they will continue with an academic career.
Thank you. I'll add also that we have a mentoring scheme for women academics in the university, and it's exactly these conversations that mentoring is about. It's about really getting all of these perspectives and saying, okay, you know, I know what I would like to do. What do I think? What do I need to think about? And finding out, you know, and talking to people with that little bit of experience, or you know, who can open doors as well, is very, very important. So, thank you. Any other questions? Yes. Oui, oui. On va arrêter parce que, oui. This is the last question.
Okay.
Thank you so much. We at the Ministry of Finance, we see the same issues as you talked about at in the more science fields, which is really not my field, I must say. So we set up the Gender Finance Task Force. We set up now the working groups, because we try to see in the finance sector where we can work on. But I was wondering if in the science fields, if there are like other structural challenges that hinder women from staying longer in their positions. If they're like, besides childcare, I must say, that for them to develop longer, if there's like really challenges there, or structural challenges that must be addressed.
I think one of the things in the United States, graduate students come and join research groups, and it's only been fairly recently that women professors have had as large groups as the male professors have. I have a woman colleague who was the director of the chemistry division of the National Science Foundation, and then has just recently been president of the American Chemical Society. And she has a research group of about 25, which is great to see. But the question of recruiting graduate students, because one has to encourage them to come and join your laboratory or your research enterprise, has in the past been not so easy for women. The largest group that I ever had is 8 people, and that's small compared with some. On the other hand, there are well-known theoreticians. Hans Andersen at Stanford usually had a group of about 3. So it's not necessarily an obstacle. But I think the question of respect from the students sometimes can be an obstacle. I never encountered that myself, and I can't really explain why. Could have been because I tended to be kind to the students, and so they were happy to have me as a professor. But yeah, I would say that the most serious challenge is combining motherhood and career, and that is truly still difficult. But since that is the last question, I'd like to say again, thank you very much for the opportunity to speak here. It's just been a tremendous experience for me, and I'm extremely grateful to the Bridge Forum Dialogue and to the people at the Institute for Advanced Studies. I'd like to recognize especially Dimitri, Alexander, and Drew, who are here in the audience, for wonderful experience that I've had working in the Department of Physics and Materials Science. It's been absolutely tremendous for me.
Thank you very much. I'm afraid we don't have any more time because we've actually lost sense of time and gone over time. So thank you very much indeed, Professor Hunt. Thank you for this very, very exciting evening. Thank you. And thank you.